from the beginning of the alphabets. These are variables. Lowercase letters from the beginning of the alphabets. These are terminals. Lowercase from the end of the alphabet. These are words over the terminals. And then lowercase Greek symbols. These are arbitrary strings over N union T. So these can contain variables, they can contain terminals, and so on. Now we've defined a derivation. If we have A goes to gamma is a production, and we have alpha and beta arbitrary strings, including epsilon, then alpha A beta derives alpha gamma beta. And then the reflexive intransitive closure, which is just a fancy way of saying we're doing that 0 or more times, is then simply what we're doing when we derive in several steps. And then if we have a grammar G, then the set of all words generated by the grammar is the set of all strings W that can be derived from the starting symbol. And so I've showed you the grammar given basically by the set of productions. Obviously, little a and little b are the terminals. Capital S is the only variable. That means S is obviously the starting symbol. And so we have these two productions, and that grammar then generates a to the n, b to the n, n greater or equal to 1. These are the only strings that are over the terminals only. So if we go back, we've done finite automata.
Professor, I wasn't done writing the other part on the other side. Is it all right if we go back there for a second?
There you go. All right. So if we go back to what we were looking for, or what we were looking at when we did finite automata, well, we had DFAs, NFAs, regular expressions, language equations. What we haven't done yet are grammars. If you recall, I did talk about grammars as well. And so what we want to define are regular grammars. Now, the grammars that I've written down here are context-free grammars. Okay? Now, the only difference that we have when we deal with regular grammars, well, this is NTPS, just like before, with the only difference being that if P is a production, then P is either A goes to little a, capital B. So capital A and capital B, according to our convention, if you recall, are variables. And little a is a terminal, single terminal. So this is one possibility, or P is equal to A goes to little a. So clearly, if you go back to the context-free grammars, then A goes to alpha is how a production will look. Now we're going to restrict that alpha to be either a single terminal followed by a single variable, or a single terminal. It turns out that these are grammars that will generate precisely regular languages. So if R is a regular language, we have to throw in one little technical condition, and epsilon is not in R, then there exists a regular grammar G such that L of G is R. So that means we're looking at productions of this type. And that's, of course, the reason why we have to exclude epsilon, because clearly there is no way we can generate an empty string using these two productions, these two types of productions. So let's look at why this is the case. Say we have a NFA, it doesn't make any difference. Suppose we have Q0, Q1, Q2, A, B, Q1, Q2, Q0, Q1, and nothing, Q0, nothing, and 1, 0, 1. So suppose this is an NFA we're given. So how do we get a grammar that behaves essentially the same way as the non-deterministic finite automaton? What we're going to do is we're going to define S0, S1, and S2. And those would correspond to those states. So the variable of the grammar S0 will correspond to the state Q0, S1 to state Q1, and S2 state Q2. Now there is something else we have to add at some point, but let's just go look at this. So S0 generates, well, A S1. That corresponds to the fact that if I'm in state Q0, I can get an A, and then I will be in state Q1. So I have this variable S0, and then I have A, little a, and then I have S1. And then the similar situation for Q1. we have A and S2, which corresponds to Q1 under A going to Q2, or B is 0, which corresponds to Q1 under B going to Q0. And then the Q2 gives rise to the S2 productions. We have A goes to S0. This is that transition Q2 under A to Q0, or under A to Q1, which is S1. So this is perfectly mechanical. The only thing that we have to worry now is that there are some accepting states. Come on. So we have Q0, an accepting state, and Q2, an accepting state. How do we capture that? Well, in the automaton, if we are in state Q1, for instance, and we go to state, we have an A, we go to state Q2, and that would be possible that we finish there. Okay. So instead of having the situation where we continue with the S2, A and then S2, we actually want to say, all right, it is certainly possible that we're going to finish at this point. Q2 is an accepting state, and therefore we're going to be finishing here. So that means that S1, this variable, which corresponds to the state Q1, could take this production, which corresponds to the transition Q1 under A to Q2, and then finish there, which means in order to mimic that in the grammar, we just have A. So if we were to take the transition from Q1 to Q2 and then finish, do not continue taking transitions, but end up there because Q2, of course, is a final state, then that would correspond to S1 goes to A. And similarly, Q1 under B goes to Q0, which is an accepting state, and therefore it would be B. So,
Professor.
Yes.
Okay, so at this point, I just want to, we're trying to prove that, like, well, actually, you're demonstrating that a grammar can translate to a regular expression.
No. A finite automaton can be transformed into a regular grammar.
I see. So this is
so we're given this non-deterministic finite automaton, and now I'm constructing a regular grammar that basically does exactly the same thing that the finite automaton does.
And in this situation, S1, because it doesn't have an accepting state.
Well, that's not the issue. Okay? The issue is that S1 can go to, well, Q1 can go to Q2, and Q2 is accepting. And so that means if I want to go S1 goes to AS2, well, the S2 means I have to do something with the S2. But I don't want to, because I'm taking the transition Q1 to Q2, and I'm going to stop there. So I need S1 goes to A. And similarly, because Q1 goes to Q0 under B, I could, of course, go S1 goes to B S0, which means now I have to continue with whatever is S0 doing. But if I wanted to stop there and say, well, Q0 is an accepting state and I can stop there and the word is accepted, then of course I'm going to go S1 goes to B. And now, looking at this, Q0 goes to Q1. Q1 is rejecting. I don't have to add anything. Q2 goes to Q0. And so that is a possibility under A, so I need that A. Because if I go Q2 under A to Q0, I could say, all right, I'm going to stop there and not go any further. Then I need S2 goes to A. On the other hand, if I go Q2 to Q0 and then I continue there, then I have, of course, S2 goes to A, S0. Q1, of course, is rejecting, and therefore there is nothing to be added. So these are, in fact, the productions of the regular grammar that almost generate this language. So if we have this language, this is our R, then this grammar, the grammar, with S0 being the starting symbol, and A and B being the terminals, and S0, S1, S2 being the variables, generates almost exactly R. Well, what does it not generate? It obviously does not generate the epsilon. This regular language, the language defined by that non-deterministic finite automaton, has the initial state Q0 accepting, which means that epsilon is in R. Now, we can't do that in the regular grammar because there is no way to generate epsilon. So what we can see then is that this is exactly R minus epsilon. So we generate everything except the epsilon. The epsilon is, of course, accepted by this non-deterministic finite automaton, but there is no way that this can be done with a regular grammar because in order to generate epsilon, you need to have a production that generates epsilon. And obviously, this is not permitted in the form of the productions for a regular grammar, and therefore the thing that we can't generate is the epsilon. Everything else we can generate. So this shows that if we have a regular language and epsilon is not in the regular language, or else we just take it out, which is what we have done here, then there exists a regular grammar that generates that language. And you can go back and take a regular grammar and construct a non-deterministic finite automaton. This is almost exactly the same way. So let's perhaps look at an example given a regular grammar. G, there exists an NFA N such that the language accepted by that non-deterministic finite automaton is exactly the language generated by that grammar. So if we have, we can just do that in general. We have A goes to little ab, or A goes to little a. So if the production A goes to AB, then you have A tau of A and little a contains B. Well, this is a non-deterministic finite automaton. So B is an element of tau of A and little a. There may be, of course, A goes to AC, in which case you would have C in that, and so on and so forth. And in that case, if A goes to A, then we have a new state that is in tau of A and A, and this square state is the only accepting state. So if we have a grammar G in TPS, then the non-deterministic finite automaton is obviously the alphabet of input symbols is T. The states are all the variables of the grammar plus this special state. We have tau, which is defined that way. We have S, which is our starting symbol, and the only final state is the state that's square. So let's look at a complete example. We have, say, S goes to A, or A, B, and A goes to A or A S, and B goes to B or B or BS. Okay, so that means we have T, so our non-deterministic finite automaton obviously is A and B. That's the input symbol. Then we have the S, A, B, and that square. Those are the states. We have tau, which I'm going to do in a second. We have S, and we have the square as the only final state. And so now tau, we have S, A, B, and the square. And we have little a and little b. And of course, S is the starting symbol, but that's already clear from that. And now I have this. So that means that A is here. And according to this again, there's B here. Now I don't have any S goes to B, so there is nothing here. Then I have A goes to A, which means I have the square. And A goes to S, so I have the S, and there's again no B. And for B, well, I don't have anything. For capital B, I don't have anything under A. And then I have the square from that production. I have the B from that production, and the S from that production. And the square doesn't go anywhere. And so if you want to write this down completely, then you have the square is the accepting state, and the rest are rejecting. So that shows you that given a regular grammar, you can always find a non-deterministic finite automaton. And so assuming that the languages that we are considering are such that they don't contain the empty word, we've now established that regular grammars do exactly the same thing, generate exactly the same languages as are accepted by finite automata, non-deterministic or deterministic, or are denoted by regular expressions. So the only wrinkle when it comes to regular grammars is that we can't handle the empty word. But the empty word is a little blip. So if you ignore the empty word, then regular grammars, finite, non-deterministic finite automata, and deterministic finite automata, and regular expressions define exactly the same languages. So, now I'm
Professor,
already
on the previous
Yes,
slide, I just want to get a little bit of clarification.
yes, sure.
Um, on top it says such that the language, the NFA is equal to the language grammar, correct? Is that how you
Right.
would read that?
The language accepted by the NFA that we're constructing is equal to the language generated by the grammar. So this is the grammar, and this is the NFA that we construct. And this grammar generates exactly the language that this NFA accepts.
So now we're going into more complex commands with the grammar, and we can actually transfer them into NFAs.
Right.
Which
We can, once you have a grammar, a regular grammar, you can translate that into NFA, and you can then translate that into DFA, and so on and so forth.
Okay, so at this point you can add, it's basically like being able to, any grammar-based question can be transferred into NFA, and then the NFA can say whether or not it is an accepting state or not.
Correct.
Okay, continue. Thank you.
Okay. Any other questions? All right. We've already laid the groundwork for blatant discrimination against the poor little epsilon. Well, let's continue discriminating. Epsilon is the kind of thing that we're going to try to get rid of. And, well, what we're going to look at is epsilon productions. We're back to context-free grammars. And so a production is A goes to alpha. Remember the convention, capital A is a variable and alpha is a string over the terminals and non-terminals. That's what we had here in the convention. Variables, terminals, words over terminals, and arbitrary strings. So we're using that. A goes to alpha is precisely the way a production in a general context-free grammar looks like. So that in particular allows the alpha to be epsilon. There is nothing that says the alpha can't be epsilon. So in general, a context-free grammar may have productions that are of this form. Variable goes to the empty word. And now what we want to do is we want to eliminate epsilon productions. Now, that, of course, is an issue that is a little bit fraught, because we have already seen in the case of the construction of a regular grammar for a given finite automaton that we can generate everything except the epsilon. So now if we want to eliminate epsilon productions, we are given a context-free grammar G in TPS, and we want to get rid of all productions A goes to epsilon. Now, that, of course, you should immediately see that if epsilon is in the language generated by that grammar, then there's no way we can generate epsilon if we get rid of all epsilon productions. So what we really then can do is we can eliminate the epsilon productions for L of G minus epsilon. We obviously won't be able to generate epsilon if we eliminate all epsilon productions. So if the grammar does not generate epsilon, then of course this is not a problem. But if the grammar does generate epsilon, then having eliminated all epsilon productions would then clearly preclude us from generating epsilon, so we can generate everything except epsilon, which is of course very much akin to what we did when we constructed a regular grammar for a given NFA. We can generate a regular grammar only for the language minus that epsilon. And so that is again the same situation that we have here. And so given this grammar G, we're going to construct a new grammar, G prime, which will be N prime. It will obviously have the same terminals, new set of productions, and can have the same starting symbol. So let's see how we're going to deal with that. If I have an epsilon production, well, I want to get rid of it. If this is the only A production, so this is the first case. If we look at all the A productions, and this is really the only A production, there's nothing else. Okay? In that case, replace A by epsilon in all right-hand sides. Of all productions. That is not really very deep, because if the only thing we can do with A, capital A, is generate epsilon, and obviously we have to do that because clearly the language that we are interested in is the language of all words that can be derived from S that do not contain any variable. So clearly, in order to get a word in that L of G, that language generated by the grammar, we have to get rid of the A, because this is a variable. And if A goes to epsilon is the only production for that variable A, then obviously instead of applying the A goes to epsilon to a right-hand side that contains that variable A, I can just replace it immediately. So if I have B goes to A, or A, B, C, then I'm going to replace that by B goes to little a, because there are these two capital A's that eventually will have to be removed. The only way to remove them, if A goes to epsilon is the only A production, is to replace both A's by epsilon. So that means the only thing that's left, having replaced this A and that A by epsilon, is the little a. And then the other A, well, we do the same thing. So we have B goes to A, B, C, A or B, C. So in that case, that's very easy. Now, if A goes to epsilon is not the only A production, then things get more complicated. So we have A goes to epsilon and A goes to alpha. There's at least one other, and it is whether there's 1 or 59 doesn't make any difference. The issue is it's not the only A production. In that case, we have to systematically replace or not replace that A by epsilon on the right-hand sides. So let's take the same B goes to A, or A, B, C. Well, now we have two possibilities. Either we use A goes to epsilon to get rid of the A. Remember, eventually we have to get rid of the A because we want to get a word that is generated by the grammar, and that word then has to be over the terminals alone. And so that means that the A, capital A, has to be gotten rid of. So we can either replace it by epsilon, or we can replace it by whatever else A generates. So in that case, if we replace the A by epsilon, then we have B goes to A. If we replace the second A by epsilon, or, little a, capital A, if we replace the first A by epsilon, or both. So that follows from this. And then we have the other one. We have, if we replace the capital A by epsilon, we have BC. And if we don't replace it, we have ABC. And now we can get rid of the A goes to epsilon, and the only thing that is left is A goes to alpha, or alpha 1, alpha 2, etc., etc. So let's look at an example. Suppose we have S goes to A, B, S, or A, or epsilon, or A goes to B, A, B, 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 or epsilon, and B goes to S, A, S, B, S, or epsilon. So obviously, this is not a particularly interesting language. It just is there to show you how we can eliminate epsilon. Now, this will create some problems because obviously we are now looking at a situation where the L of G, if you look at that, generates epsilon. So when we now construct a new grammar, then that new grammar will be only for the language L of G minus epsilon, because clearly that epsilon can't be generated if we eliminate all epsilon productions. So this, we have to go systematically through that. So let's look first at the elimination of S goes to epsilon. There is only one production where S occurs on the right-hand side, and so that gives us B goes to, well, there are 3 S's. Now, the problem with that is, of course, that we basically, for each of those 3 locations, we either replace the S by epsilon or we don't. Which means that there are 8 different production, right-hand side of the production B, that arise from that first production B goes to SAS, because for each of those 3 locations, I can replace the S either by epsilon or I don't. So if I don't replace any of the S's by epsilon, I keep that. So now let's replace the first one by epsilon. Then I get this, ASBS, or I replace the second one, or I replace the third one, or I replace the first 2, or I replace the first and the last, or I replace the last 2, which is, or I replace all of them by epsilon. So I have 1, 2, 3, 4, 5, 6, 7, 8, which is of course what I need, because that is, I have 3 places, 1, 2, 3, and each of those 3 places then could either be replaced by epsilon or not. So that is, in general, if I have n places, then obviously I have 2 to the n different ways of doing that. And so in this case, of course, it is 8, because 2 to the 3rd is 8. And so then I have epsilon. So this is now the new B productions. The new A productions, there is no change. And the S is now A, B, S. There is an S. I can replace that S by epsilon or not. And so if I don't replace it, I have ABS, or I have AB if I do replace it. And then I have A. That comes from that. And the S goes to epsilon now is gone. And so let me just copy that over. So this is eliminating S goes to epsilon. Okay. Now I have an A goes to epsilon. So I want to work on this one. That means I have to look at all the A's. I have an A production here, an A in a right-hand side of a production here, an A here, and two A's here. Okay, so there are no others, but if there were, then I would have to do the same treatment for them. So I have S goes to, well, if I don't replace the A by epsilon, I get A BS. If I do replace it, then I have just BS. So that takes care of this first production, S production. Then I have S goes to AB. If I don't replace it, I have AB. If I do replace it, I have B. And finally, I have here two A's, capital A, little a, capital A. So I will get four productions because there are two locations where I either replace it by epsilon or I don't. And that means I get four productions. If I don't replace the A by epsilon, either one of them, I get A. If I do replace the first one, I get little a, capital A. If I replace the second one, but not the first one, I get capital A, little a. And if I replace both of them, I get little a, nothing else. So that then takes care of the elimination of the A goes to epsilon. So this one is gone now. And so I have left A goes to BABB. And I have this, oops, no, I don't want the red. I have the B, which is SASBS, and so on. Well, let me write it down completely. Doesn't make much difference. Just copying over. So we have now managed to eliminate the second epsilon production. And now we have to eliminate the third epsilon production. B goes to epsilon. And so we will then get this. There is no capital B in this set of S productions. There is no capital B in this set of B productions, so eventually we will get rid of the epsilon. But there is obviously a bunch of B's on the right-hand side of the A production, so we have three positions, which means we will have three places where we can either replace it by epsilon or not. And that means that we will have, again, 8 productions. If we don't replace any of the B's by epsilon, we have BABB. If we replace the first one, A, B, B, B. If we replace the second one, B, A, B, B. If we replace the third one, B, A, B, B. So that's one of the three. Then we'll replace 2 of the 3. So we have, say, the first and the second one, A, B, B. Or the first and the third one, A, B, B, or the second and the third one. And finally, we can replace all of them, all capital B's by epsilon. So this is 1, 2, 3, 4, 5, 6, 7, 8. And so that means we now got rid of this epsilon production. And so the final result then is this. And that. And that. And so what we have here is a new set of productions that will generate everything except epsilon. Obviously, there's no way to generate epsilon because epsilon does not occur on the right-hand side of any production, but everything else is generated because we provide all possibilities that one can carry out derivations in, except, of course, the s goes to epsilon. So that s goes to epsilon, that can't be done, s being the starting symbol, but everything else can be done. So in this way, we now have, so the blue would be G prime. Technically, I probably should call all these productions S prime, A prime, the variables S prime, A prime, and B prime, because these are obviously different from the ones that I have up there, but that I think you can easily make that connection. So this is now the new grammar G prime that has the same variables S, A, and B. It obviously has the same terminals, little a and little b. It has S, still the same starting symbol, but it has definitely different productions. A lot more. So we had 1, 2, 3, 4, 5, 6, 7. And here we have 8 and another 8. So 24. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. Oh no, one more. 1, 2, 3, 4, 5, 6, 7, 8. No, 24. Okay, everybody clear what we have done?
Yes, sir. Could I look at something on the previous slide?
Sure.
I have a question if I... So there, on the very bottom, when you have your B goes to A, big A, little a, big A, on the left side there. On the,
this one.
Yeah. So on that right side.
This one.
Yeah. Where it says B goes to big A, little a, or little a, big A, yes, there. Shouldn't that set also include if epsilon isn't in it? Would it also include big A, little a, and big A?
Oh, you're absolutely right.
It does. Okay, I just thought. Okay.
No. You are right. You're right. I only showed you what happens when you replace any of the A's by epsilon. If you don't replace them, that's of course AA.
Which you did many times on the next slide.
I did in this. I just
okay. So
the explanation I've given you was that I was going to replace any of the A's by epsilon. Now this of course means I'm not replacing any of the two. So if you want to get it complete, then obviously B goes to AAA or AA or AA or A. and then we have the same thing. Well, here I kept it, so yeah.
Okay. And then the next page is exactly right. Okay, I get it.
Right.
I'm sorry.
Okay. No, you're absolutely right. This should go in here. This means there is no a, no variable a is replaced by epsilon, which is of course what we have here. The a is not being replaced by epsilon, whereas here that a from the second production was replaced. Yeah, thank you.
That requires double points, right? Points on the exam.
Any other questions?
Professor, on slide 5.
5, okay.
I just wanted to clarify, when you're moving the epsilon on S, for B, the reason why epsilon is still at the end because you haven't removed it on the, for B, right?
What I did was I first took S goes to epsilon. I wanted, the first step in this case was getting rid of S goes to epsilon. So what I did then was I looked at where does the S occur, because the S obviously either has to be replaced by epsilon or it stays. And so there is only one production. B goes to SA, SB, S, where the S occurs on the right-hand side. If there had been another one, then there would have been more work, okay? But in this case, we have only one production with the S, and so we take that S and either replace it or we don't by epsilon. So here we don't replace any of the three S's by epsilon. Here we replace the first one, the second one, the third one. Here we replace the first two, first and the last two. Here we replaced all of them. And then, of course, we still have the B goes to epsilon. So that B goes to epsilon has nothing to do with those 8 productions. The 8 productions, B goes to all of this, come from systematically replacing S either by epsilon or not. So that then allows us to get rid of the S goes to epsilon, because everything, every possibility that one can carry out by replacing S either by epsilon or not has been taken care of. So we now can get rid of this S goes to epsilon.
I have a question in terms of like the structure of the question. So right now we have S, A, and B. S being, does S represent a variable or does it represent the string? As
No,
we
capital
defined
S, capital A, capital B, these are all variables.
Okay,
The
so
left-hand side of a production is always a variable. The right-hand side is a string over terminals and non-terminals.
okay. And in here, why did we choose to get rid of S first? Or is that the question that you just answered?
No. If you want to get rid of the B goes to epsilon first, you can do that. I mean, ultimately, we want to get rid of all epsilon productions. I simply started at the top and worked out my way down. S goes to epsilon, A goes to epsilon, B goes to epsilon. So the elimination S goes to epsilon gave rise to this. The elimination of A goes to epsilon gave rise to this. And then finally, the elimination of B goes to epsilon gave rise to what I wrote down encased in blue.
Okay.
Any other questions? Well, now let's look at something that's a little ugly. Let's say S goes to A, or let's little a goes to bb or little b, b goes to ss or little c. And we're going to throw in b goes to epsilon. So what we have here is a single epsilon production, which we want to get rid of. So the way we do that is we look at the right-hand sides of the productions and replace or not replace the b by epsilon. Well, there's only one production that has a capital B, and on the right-hand side, it's A goes to BB. And so that means in order to be able to get rid of B goes to epsilon, we have to replace A goes to, well, if we don't replace any of the B's by epsilon, we still have BB. Or if we replace one of them, then we have 1B. And of course, in this case, it doesn't make any difference how we do this. We can do the first one by epsilon or the second one. In both cases, we simply have 1b. But now, if we replace both b's by epsilon, we're going to get an epsilon. And of course, we still have the a goes to b. So at this point, we have managed to get rid of the b goes to epsilon. But we introduced another epsilon production. A goes to epsilon. Okay. Now let's see. Well, we have to get rid of that one. So we have B goes to SS.
Is this going to make an infinite loop?
Yeah, well, we get to that. I promised you something nasty, so yes, it is going to be a little nasty. You sort of saw already where we're going to end up. So we need to get rid of the A goes to epsilon. So we have S goes to AA. I'm just writing everything down. So this is now the B goes to epsilon is eliminated, but we have an A goes to epsilon. So we now have to eliminate that, which means there's only one production, S goes to AA, in which the A goes to epsilon has to be applied. So that gives us S goes to, if I don't replace any of the two A's by epsilon, I get AA, or I replace one of them by epsilon, get A, either one of them. So no point in writing that A down twice, and then I have an epsilon. So now I have A goes to BB, B, and little b, and B goes to SS, or little c. And so now I have managed to get rid of this epsilon production, but at the cost of having introduced yet another epsilon production. S goes to epsilon. So now I want to get rid of this. I get S goes to AA, or A, or little a, and A goes to BB, or B, or little b, and B goes to SS, replacing none of those two S's by epsilon, or S, replacing one of them, or epsilon, or C. Let's see, it's just that. So now we have a bit of a problem, because now we have this B goes to epsilon, which of course, if you were to try to replace it the way we have done that so far, we would basically circle around again and get to this and then get to this. And so clearly this would not terminate, because we will always get another epsilon production, which led one of your colleagues to suggest that this gets us into an infinite loop. And yes, that's basically the problem. And how do we fix that? Well, we're going to be ruthless. We have to remember, and that is important here, you can't just do it one step at a time. We have to remember that we've already eliminated b goes to epsilon. And therefore, when b goes to epsilon pops up again, we just get rid of it. And so the answer then is S goes to A little a goes to B, B, little b, and B goes to SS, little s, or little c, and that would be the answer. So that popping up B goes to S productions, B goes to epsilon production, that occurred after we've gone through all that. And at that point we have to remember we've already gotten rid of B goes to epsilon. So there's no more point in trying to get rid of B goes to epsilon, because everything that can be done with B goes to epsilon has already been taken care of. And so that then is the answer to the question, will this terminate? Yes, it will, because we break the loop. There is no further work to be done, because, as I said, we've already eliminated all the contributions that the B goes to epsilon production can make. And so there's no point in doing it again.
Professor, I'm a little lost. If we can step through this one more time, right now.
Sure.
Yeah, you went
all right.
through.
We start out with this, including all the B goes to epsilon. Okay, so this is the starting point, including the B goes to epsilon. From that, we went to this one. What did we do here? Well, we got rid of the B goes to epsilon. And that means we had to replace all the capital B's in all the right-hand sides, which in this case happens to be just one production. A goes to BB. We had to replace that BB systematically either by epsilon or not. So if we don't replace either of these two variables B by epsilon, then we stay with BB. If we replace one of the two, doesn't make any difference which one, because there's nothing in between, so we get 1B, and if we replace both of them, we get epsilon. And then we also have that B. A goes to little b, that stays there, and so we have that. So that then is this result, which of course now surfaced the A goes to epsilon production, which we didn't have before, but that was a consequence of replacing both b's by epsilon. So we got rid of the B goes to epsilon, but we now have an A goes to epsilon. And then we constructed this by getting rid of A goes to epsilon, by sticking in all possibilities for the variable A. Well, there's again only one right-hand side, S goes to AA, and so if we don't replace any one of those two by epsilon, then we stay with the AA. If we replace one of them by epsilon, we get an A, and if we replace both of them by epsilon, we get epsilon. And of course, we still have that A. So that gives us the S goes to epsilon, which of course we never had before. And so this is then this result. And then finally, we get rid of the S goes to epsilon, which means there is B goes to SS. So this is the same, except I get rid of the epsilon. This is exactly the same. And then the B, well, B goes to SS if I don't replace either of those two S's by epsilon. It is B goes to S if I replace one of those two S's by epsilon. And it is B goes to epsilon if I replace both of these two S's by epsilon. And then, of course, I still have that C. And at that point, then, we're going to break that loop. We observe that we've already eliminated B goes to epsilon. And when I say eliminate, that basically means we have provided all possibilities that one can provide by using B goes to epsilon. Since we've already done that in this, from here to there, there is no point in doing it again.
Is this the equivalent of the DFA?
No, it has nothing to do with the DFA.
Well, you know, in the system, whenever you see it again, and then you're like, you have 1, 2, 3, 4, and then it does it again, then we stop there. Is that the kind of thing we're?
But in the in the NFA, we just stopped because there was no point in continuing. In this case, you could continue, but you won't get anything new.
So it will just evaluate the same thing over and over if you were to continue it. Okay.
Exactly. So there's no point in doing it again. I mean, remember, we've eliminated B goes to epsilon. How did we do that? We provided all possibilities that the exercise of the production B goes to epsilon will afford us. And so there is no point in doing it again because we have already done everything that can be done with that. And therefore there's no point in doing it again.
Okay, got it.
All right. So, well, I guess on today's Monday, on Wednesday we're going to look at another elimination. This is in some sense easier, in some sense more complicated. If we have a production A goes to B, that means you have a variable that generates another single variable. This is called a unit production. And just like we didn't appreciate epsilon productions, we also don't appreciate unit productions. And anytime we don't appreciate something, we get rid of it. So on Wednesday, we will do elimination of unit productions. And then we have one other step that we have to carry out, and that is...
I'm sorry, sir, I have a question about this last, one more question on this last topic we were just covering.
Let me just finish. We on Wednesday will eliminate unit productions, and we will also eliminate useless symbols. All right, what's your question?
I just want to make sure. I suspect that it wouldn't be possible for us to get back to a repetitive reduction without going through all the other ones first, right? Is there a case where we could get back to B again without going through S and A in a different setup? Would that be possible? Or we would always have to step through them all before we get back to the duplicate reduction?
It can, whatever grammar you have, you just eliminate the epsilon productions, and then you'll see how it works out. I mean, in this case, I picked a particularly insidious one, in which case the epsilon, you start out with one epsilon production, and you get another epsilon production, and you get another epsilon production, and then it cycles back. But that's not necessarily always the case. I mean, but yeah, there are all kinds of nasty little surprises that are possible. But what is important is that once you have eliminated a particular epsilon production, there is no point in trying to eliminate it again. If that epsilon production pops up again, you don't have to eliminate it. So in this case, we had the B goes to epsilon, which we eliminated going from here to there. And then when the B goes to epsilon pops up again, there is no point in doing it again, because whatever functionality that B goes to epsilon production would afford us has already been provided.
Okay. So if we reach a repeat, but there's still other variables.
Oh, then you have to get rid of the other ones.
Of course, yeah, and that could happen.
But remember, you will only have at most one epsilon production per variable.
Right. Okay. So yeah,
which just a preview is not true for unit productions.
Okay.
Unit productions are nastier from that point of view because you can get many, many more. But on the other hand, it doesn't change the language, whereas in the case of the epsilon productions, it does change the language because you're basically looking at the language minus the empty word. That's not what it will happen with the unit productions. Okay? Any other questions? All right, then we will talk. I will talk to you on Wednesday. All right. Have a good afternoon. Bye-bye.